Hello students, Sean McMahon here. So in this video, we're going to continue our discussion on naming compounds. And if you're following the format, you just finished going over naming binary covalent compounds, or you can think of it as binary molecular compounds. Well, there's a special type of binary covalent compound, and those are binary acids. And a lot of times people, when they hear the term acid, they get really nervous or freaked out. But acids are pretty much everywhere. So in this example of citrus, we have citric acid. And if we notice, every vertice here is a carbon. So we have carbons all along here. Carbons are 4 away from group 8A because they're in 4A. So they like to form 4 bonds. So we see that this carbon here, it has 2 bonds to the oxygen, 1 to this oxygen, 1 to this carbon. If I go to this carbon here, this is a line formula. They don't show the carbons and the hydrogens that are not in what are called functional groups that are part of the skeleton. They don't show them. So what's missing is this carbon only has 2 bonds. So what they're not showing you is there's 2 hydrogens right there. And then if I look at this carbon, it actually has 4 bonds, 1 right here, 1 to that carbon, 1. So it has 4 bonds, right? And then if you look at this carbon, it's like this one over here, this group right there, right? And then this carbon's missing a couple hydrogens because it's line formula. And then this group here. But for the most part, what I want to show you is this is not a binary acid. Why? There's carbons, hydrogens, and oxygens. But it is an acid, and it's not that bad. I mean, citric acid tastes a little sour, but for the most part, it's okay. Well, here's another acid. If you look at this acid, right, it's acetic acid. This is one you need to know. And 5% of vinegar is 5% acetic acid. If you look at this, it's also like the citric acid here where it has, your carbons and your hydrogens, right? But one other thing I want you to notice that it's an oxy acid. Both of these are considered oxy acids. The other thing that I want to really emphasize is they both have this group here. This group, where you have a carbon double bound to an oxygen and then to another oxygen and a hydrogen's bound to that, that's referred to as a carboxylic acid. You may have heard this. It's on one of the ends of an amino acid, right? When we talk about the citric acid cycle or the Krebs cycle, those are basically carboxylic acids that are 2 to 6 carbons in length. In fact, all of our nutrients, right, your lipids, your carbohydrates and proteins can be converted into carboxylic acids that feed into the Krebs cycle. But essentially, carboxylic acids are weak organic acids, but they're oxy acids. So there's 3 elements, carbon, oxygen, hydrogen. We're talking about binary. So what's binary? 2. So what is this? This is hydrochloric acid. Now, a lot of you know that that's found in gastric juice, right? It facilitates the digestion of proteins. But the way it's drawn here, it's obvious it's binary because there's only 2 elements. And we see that we have a hydrogen, okay? And the hydrogen, again, if we follow, if we talk about our rules, its outer shell, its valence shell has 1 electron. That's in group 1A. And chlorine, right, its outer shell has 7. So chlorine wants 8. It wants 1 more. Hydrogen wants 2 because it wants to be like helium. When these 2 approach each other, these orbitals now overlap. And that's what a bond is. Now, I didn't draw what are referred to as lone pairs. Oops, let me clean that up. I didn't draw the lone pairs for the chlorine, but they're right there. But this overlapping of these 2 electrons, and they're being shared, they're close to hydrogen and chlorine. What happens is now hydrogen has 2 electrons by it. And the chlorine, with the additional one from hydrogen, it has 8. So we form a bond. So here's my hydrogen. Here's my chlorine. This bond is basically 2 electrons. And there's also lone pairs on this chloride. So you may have seen this in some of your biology books, drawn like this, right? But what's unique about this binary acid, and what makes it an acid, is when I put it in water, it'll dissociate, it'll break apart, and even though they're 2 nonmetals, it'll produce ions because the chlorine will take, because it's more electronegative, the hydrogen's electron, and this bond will break, and I'll end up having, right? I'll end up having a chloride ion that was stolen from the hydrogen, and what's left is what's called a hydrogen ion or a proton. Why a proton? All a hydrogen is a proton with an electron around it. So that's why the hydrogen ion is called a proton. And binary acids are basically, they're basically covalent compounds. When you throw them in water, they dissociate to give you ions, and one of them has to be a proton. So acids are special covalent or molecular compounds, and the cation is a hydrogen ion or a proton. There's 2 types, and they have different naming rules. The one type are the binary acids, binary meaning 2. For it to be an acid, it has to have hydrogen, so the other element is a nonmetal, and that's where the name is going to be derived from. And then there's the oxyacids. Those are going to have the hydrogen, a nonmetal, and oxygen. So this video is going to focus on the binary acids, but here are quite a few different types, and it looks a little intimidating, but we're going to break down the rules. So again, I'm going to focus right now on the binary acids. And there's more than just these 2, right? So here are some examples. The binary acids, HCl, hydrochloric, HBr, hydrobromic acid, H2S, hydrosulfuric. What we notice is for every acid that's a binary acid, that means it has hydrogen and a nonmetal, it has the hydro prefix, and then you cut off the ending of the nonmetal, and then you add ic acid to it. So the name is kind of derived from the other nonmetal other than hydrogen, but you have the hydro prefix and the ic acid suffix. So hydrochloric, hydrobromic, hydrosulfuric. So hydrochloric, again, it has the hydro prefix, the ic acid suffix. Hydrofluoric, well, that's fluorine. What do? We cut off the end of fluorine and we added ic acid and gave it a hydro prefix. Hydrobromic, hydroiodic, that's kind of a tongue twister. And now this one's special. I actually wrote out the full name, sulfur, right? But it still has that hydro prefix and that ic acid suffix. The only difference is you write out the full name for hydrosulfuric. Now, is there any other differences? Well, if we look at these first 4, they're all referred to as monoprotic. Monoprotic meaning they can only release 1 proton, 1 hydrogen. So hydrosulfuric is a diprotic. It can release up to 2. That's pretty much binary acids. That's all we need to know for binary acids. 2 elements, one has to be a hydrogen, one is going to be a nonmetal. It's going to have a hydro prefix and an ic acid suffix. So for naming binary acids, we're pretty much done. However, I want to talk a little bit about this hydrosulfuric acid to introduce the next thing that we'll be talking about in the next video, which is polyatomic ions. So when I look at hydrosulfuric acid, it might seem that you go straight into breaking 2 hydrogens, right, and releasing 2 protons and 1 sulfide. But there's actually an intermediate step, right? So there is an intermediate step. So how would that work? Well, you can kind of think of it as, here's my sulfur. It's got 6 valence electrons, 1, 2, 3, 4, 5, 6. It wants 8, so it needs 2 more. Where's it going to get it? Well, each hydrogen has 1 and they want 2. So then you get a hydrogen right here. There's 1 and there's a bond. There's another hydrogen. It's got 1 and there's a bond. Because remember, binary acids are binary covalent compounds, non-metal, non-metal. There's no charge, they're sharing electrons. So you would write it out like this in a Lewis dot format. And we haven't talked about Lewis dot structures, so just bear with me. But if we come all the way here, what happened? Basically, I took both hydrogens' electrons from it, and I ended up getting the sulfide ion. So those were the 6 that the sulfur had, but it stole 1 electron from 1 hydrogen, produced a proton, and then it stole another electron from another hydrogen. That's why all that's left is a proton, and then we get that 2 minus charge. But there's an intermediate. At one point, you just have that. So what is that? Right? Well, it's not the sulfide ion, and it's not hydrosulfuric acid, right? So when I look at this species here, this intermediate species, one of the things you got to notice right off the bat, one of the things you notice, it's got a charge. So if it has a charge, it cannot be considered a neutral compound, right? So the reason why I said compound and not element, an element is neutral, but there's only one type of atom. A compound is neutral, like hydrosulfuric acid, there's no charge on it. Compound's neutral, but it has 2 or more types of atoms. Well, this has 2 or more types of atoms, but it's not neutral. It has a charge. So what is it? Well, it's a polyatomic ion. When you have 2 or more atoms that are bonded covalently and have a net positive charge or a negative charge, you have a polyatomic ion. So really what's happening is, right, I have my sulfuric acid right here. In this bond, there's 2 electrons being shared. Well, why are they sharing it? Hydrogen has 1, he's willing to share it. If sulfur is willing to share 1, and then he has 2 next to him, so he's happy because he's like helium. Well, sulfur has 6, it wants 2. If hydrogens are willing to share, so is he, and now he has an octet. But when I throw this in water, sulfur gets a little greedy, right? Sulfur likes pulling electrons better than hydrogen. So what it can do is it can steal one of the electrons. And that's when I get that intermediate species. So I'll end up still having this hydrogen bound, 2 electrons here, but now it stole one of the electrons from one of the hydrogens. So all that's left is that proton and this species. And what is that species called? Well, that's easy. It's hydrogen sulfide. Why hydrogen sulfide? Well, it's a sulfide ion, because that's what that is, with a hydrogen attached. And the charge is only -1 because if I have a S2 minus plus an H plus, right? What's -2 plus 1? It's a -1 charge. That's why you have that. Why is it a -1 charge? It stole 1 electron, sulfur did, and it stole it from the hydrogen. So you can think of a polyatomic ion as a species. To be an ion, it has a charge. Poly, more than 1 atom. So it's more than 1 atom that has a charge. That's why it's not a compound, but it's an ion. But it's more than 1 atom. That's why it's polyatomic. And it's traveling as a group because it's held together covalently with a bond. So in the next video, we're going to talk about the different polyatomic ions, how we're going to name them, and how we're going to incorporate these charged species, and now naming different types of ionic compounds, not binary, ternary. So that's where there's more than two types of elements. So I hope you enjoyed this video, and I'll see you in the next one.